morning. I'm going to talk about the fatigue crack propagation in injection molded short fiber reinforced plastics. I'm from Japan. And the background of my presentation, short fiber reinforced plastic is one of the key materials to reduce the weight of ground vehicles such as automobile. And the injection molding process makes the high-rated economical production possible. But their application to fatigue-sensitive components are steadily increasing. And the fatigue properties are very much dependent on the fiber orientation produced by molding process and also on the test environment. And we wanted to apply the PPS reinforced plastics to the engine environment, so we want to study the effective temperature of fatigue crack propagation in PPS reinforced with short carbon fibers. This is the injection molding process. PPS is the matrix with short fiber, short carbon fiber, 38%, and we use the injection molding process to make a plate with a thickness of 1 millimeter. And this illustrates the stage of the injection molding, and so you have on the still layer the fiber aligned in this direction. We take the specimen in two directions, empty along the fiber direction with skin layer, and we call it MD, and the perpendicular direction is, we call it TD, transverse direction. And this is the exact shape of the sample. We have set the notch, drill a hole, and put a small sink, and the initial notch length is 6 millimeter. And we did a load controlled fatigue test with triangular waveform, and the frequency is 4 Hz. And load ratio is R.1, and we took the 4 temperatures. The temperature 298 Kelvin is the room temperature, and this one, and those are the expected highest temperature we wanted to use in engine environment. And the glass transition temperature of this material is 360, so we have 2 temperatures below the TG and 2 temperatures above glass transition temperature. And this is the specimen. So what first we did is considering the elastic anisotropy of the material, and we pick up this is the specimen, and we use the finite element analysis to get the energy release rate first. In MD and TD material, the crack propagates perpendicular to the loading direction, so we assume the Moldman fatigue crack propagation in this material, and we use the modify the crack closure integral method to determine the G as a function of crack length and also the loading applied load. And from G, you can calculate K value, stress intensity factor, using this equation, because this is the axis of the anisotropy is in this direction and that direction. So you can use this equation from energy release rate, you can get the stress intensity factor. And we express the stress intensity factor in the usual form. F is the friction factor. And we find it very interesting result for center-notched plate, even if a lot of anisotropy and also the influence of the temperature, so that those elastic parameter change is depending on the temperature and the direction. But still, if you plot this correction factor as a function of crack length, isotropic case, you have this one. And no influence of the for this material, there is no influence of the anisotropy. It's very interesting. So we use the K as a parameter, fractal mechanics parameter, and also we can convert using K multiply K square multiplied 8, you get G pi. And this is the anisotropic elastic constant we determined at 4 temperature. E1 is the direction of MD and E2 is the perpendicular direction. So at room temperature, you have a high E1 and very low E2. And those are the some other Poisson's ratio and shear modulus. At the high temperature, the E1 direction of M1 is reduced quite a bit. And also, depending on the loading rate, so we determine those values at the loading rate corresponds to the fatigue test. And H is a parameter, inverse H is a stiffness parameter. The stiffness parameter decreases with increasing temperature, and also the MD has a little bit higher compared with TD. So we use those H value to get the energy displayed. And this is the optical micrograph of the fatigue cracks in MD material at room temperature and also the highest temperature we measure. Those are the fibers aligned in this direction, so the loading direction in that direction. So the crack, follow the interface of the fibers, and also at higher temperature, the opening of the crack increases, and also deformation becomes in the matrix becomes bigger. And this is the case of the TD material at room temperature and also the highest temperature. The crack propagates along the fibers, and at higher temperature you have a more deformation, so the dark region increases at higher temperature. And this is the scanning electron micrograph of the specimen. MD, this is the crack goes like this, and you have some pull out. At higher temperature, deformation takes place in the matrix a little bit, but still it propagates like this. For TD direction, the crack propagates along the fiber interface and the matrix, and at higher temperature you have a large opening and also the deformation you can detect in the matrix. And if you plot the crack loss rate as a function of delta K, this is the MD direction. The temperature, room temperature is blue line, and at higher temperature is here. So those two temperatures become similar. This is the TD, so it's about the same, but at higher temperature, above TG, you have an increase of 1 order, or in this case, compared with the 3 order magnitude higher than the room temperature. And by the way, delta K is determined like this, and F is as I explained previously, this is the equation for an isotropic material. You can use this one for center notch height, and delta K is determined like this. And at room temperature, we compare the MD and TD. At higher temperature, we compare TD and MD. At the same delta K, you have a much higher rate in TD. TD is the propagation along the fiber direction, and this is the perpendicular direction. So it seems reasonable, but there is some big difference between the room temperature and the high temperature. There may be 2 reasons. One is at higher temperature, deformation increases, so the compliance increases. H is compliance parameter. Delta G, energy release rate. Delta K, stress intensity factor. At higher temperature, you have a large compliances, and you have a large energy release rate, still above TG temperature, you have the expansion of the load versus discrete curve. So the inelastic deformation takes place at higher temperature above TG. So we use the delta J. And this is the elastic part of energy release rate. This is the simplified formula for the center notch plate to determine J integral. This equation is very popular in the field of metal crack propagation at high temperature or a large deformation case. So we apply the same parameter delta J for this short fiber reinforced facets. So if you plot the growth rate as a function of delta J, the difference between temperature becomes very small. And for TD case, almost the same line. So this is the proper parameter to express the driving force of the crack propagation. But if you compare, even if the dA versus delta J, if you compare two orientations, still MD has a higher resistance. So because of the fiber is perpendicular to cross direction, so it seems to be the reasonable one. And also those differences come from the resistance to fatigue crack growth, and at higher temperature deformation becomes a little bit bigger, so the difference becomes a little bit smaller. See the fracture surface, fatigue fracture surface, empty material are room temperature, and crack propagates from left to right, and the top part, we have a line like this, and B is a perpendicular. So if the shell part, surface layer, you have a two fibers like this, and the core layer in this case is very small. So the mainly controlled by the shell layer fiber orientation, in this case like this. And so we focus the shell layer at room temperature is I've shown here, but at higher temperature you have a lot of deformation and also the TD, and again you have a deformation like this. And to conclude my presentation, the macroscopic growth path was nearly perpendicular. Microscopically, it zigzags. You have a lot of jigs there, and TD that path is less fortuitous. And if you plot the dN against delta K, you have a big difference. 2 or 3 orders higher growth rate. But if you plot the growth rate as a function TG, the difference becomes small. But still, MD is lower than the TG, even though the difference becomes very small. Thank you very much.